Alright, so here's what I think is sort of a tricky problem, and it's also another one that you can just straight up find in Folland. So we want to prove this inequality, and we're going to do it using Holder's inequality. So note that k over j, so let's see here, j and k are positive and j is less than k. So k over j and k over k minus j are conjugate exponents because if you add their inverses, then on top we're going to get j plus k minus j, so that's just going to be k, and in the denominator we're going to get k, which is, so this is 1. So by Holder's inequality, what do we have? We take the expected value of x to the j, and this is equal to, so do I have enough lines? 1, 2, 3, 4, 5. Yeah, okay, I'll write everything on its own separate line. So this is the integral of x to the j times 1 d mu, where mu is whatever. I guess this is dp because we're integrating a random variable, which means that the underlying space has a probability measure, and probability measures are denoted by p. Okay, so we have this. And so we have the integral of the product of two functions. And I guess technically you need absolute values, but I mean, it doesn't really matter because these are positive functions. And so now we apply Holder's inequality, and we'll use the k over j on the first thing and the k minus j over k on the second. So this is going to be less than or equal to, we take x to the j and we take its k over j norm. Now we multiply by the second function, which is 1, and we'll take the k over k minus j norm. And so I think this is like the trickiest part of this exercise, because it's like, how do you come up with these exponents and how do you know that they work out like this? It's sort of one of those things that you just, I don't know, I guess you could look at this and be like, okay, so we know something about the absolute value of x to the k. We want to know something about the absolute value of x to the j. So maybe we should use some we could use the fraction k over j to make this easier to work with. But I still think it's a little tricky. So anyways, so what is this thing here? So we've got the integral of the absolute value of x to the j. But because we're taking the k over j norm, we have to take the inside and raise it to the power of k over j. So if you take x to the j and raise that to the power of k over j, then the j's will cancel and you just end up with the norm of x to the k. And this is d mu. And now we have to raise this entire thing to the inverse of the type of norm we're using. So we have to do 1 over k over j in the exponent, so that's going to be j over k. And now here, for the second one, we're going to do the integral of 1 to the power of k minus j over k. Well, you're just raising 1 to a power, so it's just going to be, and of course this exponent is non-zero. Well, even if it were 0, it would still be 1. I think the main thing is that it's like, I don't know, you don't really have to worry about it. So you're just indicating 1 over the entire space. So that just gives you the measure of the entire space. And so that's the integral of the function raised to the power, but then on the outside you have to put the 1 over the exponent, so we have k minus j over k. Alright, so now what's this thing here? So this is, the thing on the left is, well, this is just the expected value of x to the k to the power of j over k. And the thing on the right, well, this is a random variable, so its domain is such that the measure of the domain is 1. So we just have, so the measure of omega is just 1, so it's 1 to a power, which again is 1. So this is all we have. And this we know is finite. So this proves that so why is this finite? This is because the expected value of x to the k is finite by assumption, and so we're taking a finite number to some exponent, which is also going to be a finite number. And so this proves that the expected value of x to the j is finite, and that directly results from this second inequality that they wanted us to show, which is what we have on the second to last line here. So yeah, and then I do also, so we're done with the exercise now, but I do want to take a little bit of time to just explain, there's a little bit more that you learn here. So in other words, so if we take this expected value of x to the j is less than or equal to the expected value of x to the k quantity to the power of j over k, and you take the if you take the jth root of this inequality, then the thing on the left is just the j norm of x. So xj is less than or equal to x. And then the thing on the right, because we'll get the j's will cancel, and so you'll be left with the expected value of x to the k quantity to the power of 1 over k, which is precisely the k norm. And so what does this tell us? This tells us that any function on this space which has a finite k norm also has a finite j norm. So any function which is in Lk of omega, meaning any function which has a finite k norm, also has a finite j norm. So this is a subset of Lj infinity. And so this is really what we prove in the fallen version of this exercise. And this is the thing that's important, is that as the exponent increases, the L as p increases, the LP space only possibly gets smaller, because if you increase p, then the space you end up with will be contained in the space that you started with. So yeah, that's useful to know. Also, this is only true for probability spaces, because you need the measure of the space to be finite, because this inequality, if the measure of the space is infinite, then this inequality that on the right here, this measure of the space raised to this power, that will become infinite. And so we don't get an inequality. And in fact, I'll have to go back and look. I think that the inclusion might actually be reversed if the space has infinite measure, but I'm not entirely sure. No, I think maybe it's reversed if the domain is like the natural numbers. I think that's it. I think if you're in like it's called like little LP, like lowercase LP. But anyways, you can look in chapter 6 of Fallen if you're curious about this. But yeah, I think this is a really important fact about this. And furthermore, what we prove in Fallen is that this bound, like, this doesn't only hold for probability spaces in which the space has measure 1. This this inequality, or this fact, holds for any space which has finite measure. And this inequality that says, like let's see here, the integral of x to the j is less than or equal to the j over k, or the integral of x to the k to the power of j over k. That inequality still holds so long as you keep that extra factor of the measure of the space to the power of k minus j over k. And so if you do the algebra and like take the jth root of that, you'll end up with like the j norm of x is less than or equal to the k norm of x times the measure of the space raised to some exponent. And so I think that's a little more general and a little more insightful, because this tells us something about how LP spaces are structured, at least on spaces of finite measure. That's really all I have to say about this exercise. And so, yeah, that's it.